Hello and good afternoon. CTS265 Section 840 students for the Fall 2015 semester at Anne Arundel Community College. This is the CCNP Route course for version 7, and this afternoon's video tutorial is going to be on Discovery Activity number 18 from Cisco Learning Labs. Again, another fantastic opportunity here to dig in and take a look at Cisco Express Forwarding. And remember from class on Monday night we talked about, we'll do a quick review here. We talked about the three different switching processes, and let me go ahead and get rid of that. Let's make this a little thinner here. Talked about the three different ways that Cisco performs switching. The legacy method, and the first way that Cisco came up with switching packets, was process switching. Now, one of the drawbacks with process switching is that every packet would hit the CPU, right? And there was no caching of any kind in use with process switching. And so you could definitely see the immediate challenge here is that when you had routers with very large routing tables, or that were processing and switching multiple packets, or hundreds of thousands of packets, if all of those packets had to hit the CPU in order to be processed and properly routed, then the CPU is really going to be your limiting factor in process switching. Now, one of the other challenges with process switching is that, again, and actually I think we already said it, it didn't have any caching mechanism whatsoever, and so this was very CPU intensive. Now, when we talk about process switching, Cisco used process switching briefly in the early 90s and then transitioned and really sort of used a computer science technique in order to solve the challenges that they were having with process switching, and they went with fast switching. Now, one of the advantages of fast switching was the creation of the fast cache. And remember that the fast cache was simply a caching mechanism where once the packet was process switched, so every first packet had to be process switched, but when it got process switched, the information that was inside the packet would then be placed into the fast cache, so that subsequent packets that would show up looking to go to the same location, they would then be able to access this fast cache, and this kind of solved the short-term problem with process switching, where you now had a cache. It could switch much quicker the packets internally, and that's a really good point. When we talk about switching, we're not talking about switching in the sense of a layer 2 switch. So when we're talking about routers in the switching, it's basically the switching of a packet from the ingress or input interface, or the inbound interface. It's the switching of that packet to the router's egress or output interface. And that's when we're talking about switching in the context of routers, that's what we're talking about. So don't confuse this with terms that you may have seen, which are store and forward, or cut through. These are layer 2 terminology. So these do not have anything to do with what we're talking about when we're talking about routers. And so again, with the fast cache, you had this increased performance, and literally with fast cache, while the packet was being process switched, the fast cache entry would be created, because remember, the first packet still had to be process switched. Okay? Now, fast caching is great, and when you think about it, we talked about process switching and fast switching when we were in your CCNA curriculum, and we also talked about CEF switching. But with respect to process and fast switching work great as long as there's not a ton of turnover in the fast cache. And what I mean by turnover is, remember, the first packet that comes in, it gets process switched. All subsequent packets are going to hit the fast cache. Now, as long as your information, your routing information, is pretty much static, and if you think about it, for the majority of the enterprise environments, how often are you going in and changing all of your routing table information? You're really not. So for the most part, the routing table is going to be static. And there may be minor changes, but where would that not be the case? What kind of an environment do you think you could find where the routing information is constantly being churned and turned over? Exactly, on the internet, right? Now the internet, as of the last time I checked was a couple weeks ago, is closing in on 575,000 IPv4 routes. And information on the internet, specifically the routing information on the internet, is constantly changing. So fast switching, while it's not the worst thing in the world for an enterprise environment, is going to be not the solution that you would want for the internet. And it was based off of that, off of that experience, where Cisco, right around 95 or 96, whoops, let's get rid of that there, right around 1995 or 1996, came out with CEF, or Cisco Express Forwarding. And so what did CEF do that fast switching and process switching didn't do? Well, for one thing, it pre-built all of the tables that it was, or pre-built the routing information and placed it into two primary tables. You had the Fib, or the forwarding, and I'll put information base, and then you had the adjacency table. And both of these tables are pre-computed based off the information that exists in the routing table, right? And the adjacency table, they also refer to the ARP cache. And so this was a major advantage of Cisco Express Forwarding over the legacy switching mechanisms of process switching and fast switching. So let's go ahead. I'm going to leave that on the screen for right now, and we're going to start with step one in the lab. It's asking me to inspect the Fib, right, the forwarding information base and adjacency table on the HQ router. Now those are two separate tables. So to see the Fib, or the forwarding information base, we simply type show Ip Sef. Now this is going to show us a bunch of different output here, and as you can see, we have some entries that are listed as drop, or no route, receive, attached, and so we'll talk about those in a second. So we also want to take a look at the adjacency table, so I'm just simply going to say show adjacency, and as you can see, there's no output right now. So let's go ahead and really quickly discuss here the Fib entries that we see. Let's switch over to yellow here for this conversation, and we're going to talk about the routes that are listed here that say drop and what that means. So these are basically the Fib flags, right? So these are flags on these specific routes. So when any traffic comes in destined for these specific routes, that traffic is going to be dropped. Now, if we take a look at the receive flag, the receive flag, which we see here, we'll look at these three entries right here. The receive flag for these three entries, when we do the show Ip Sef command, is basically indicating that the address is configured on one of the router's interfaces somewhere. So look again here, right? You see all these receive entries, and there's quite a few, that somewhere these entries are configured on one of the router's interfaces. So basically what's going to happen is that that packet is going to be processed, and then it's going to be forwarded along its path. So let's go ahead and take a look and see if I clear, and actually let me drop back just these handful of entries here. So if I were to drop back now and say show Ip Sef, and let's take a look at one of the receive entries. So 10.10.10.0, and it shows a /32. So 255, 255, 255. And it says receive for Ethernet 00. So if I say show run interface Ethernet 00, you can clearly see right here that the IP address is set to 10.10.10.1, which is in the subnet 10.10.10/32. Or I'm sorry, /30, which is, we're looking at the attached. And that's what the attached means, is the attached means that it's directly attached to an interface on this router. So this next hop field actually is a flag field telling the fib what it's supposed to do with packets that it receives for these specific routes. Now, the adjacency table contains no entries, and that's because the adjacency table is inextricably linked to the ARP cache, or the ARP table. Now, we haven't generated, there's no traffic has been generated of any kind at this point, therefore, we're not going to see anything. But that's about to change. Let's go ahead and ping 10.10.10.2, which is going to be over on the branch 1 router. So on the branch 1 router, if I were to say show IP route or show IP interface brief, you can see that we are 10.10.10.2, and this is a very straightforward diagram, right? Direct connection between two routers. So we say ping 10.10.10.2, and the first packet failed, right? We see that period there. And why does that first packet fail? Well, because we had nothing in the ARP cache. So if I were to say show IP ARP, you can see that the 10.10.10.2 entry has been in here for less than a minute, which means when we pinged, it actually ARPed out, right? It does an address resolution protocol, basically saying, hey, I know the layer 3 address. Can somebody help me out and tell me what the layer 2 address is that I'm looking for, based off the fact that I'm trying to get to this layer 3 address? And the branch 1 router responded back and said, here is the MAC address that you need to use to get to the 10.10.10.2 IP address. So now subsequent pings are going to work without a problem. All 5 packets are going to go through, and it's not going to be an issue because now we have an entry in the ARP cache. So, and in the ARP table. So now out of the ARP table, if I were to turn around and say show Ip Sef, do we have an entry for 10.10.10.2? We do. And you can see that that new entry is right here, and it says attached. Because again, that network is directly attached to this router's interface. So if we scroll back up, was there an entry for 10.10.2 earlier? There was not, right? Because again, we hadn't run the ping command, we hadn't exchanged any traffic, therefore there was no entry. Now when we do the ping, now we have an entry here, 10.10.10.2/32, and it is attached. Again, directly attached to my Ethernet 00 interface, which is this interface right here, because this is where the .2 sits. Okay, so we've gone ahead, we've taken a look at the Fib, the forwarding information base, with the show Ip Sef command. We looked at the adjacency table with the show adjacency command. And now that we actually have something, let's say show adjacency. And so here we can see the adjacency out Ethernet 00, and the address is 10.10.10.2, and it looks like it's been referred to at least 7 times, and that's the 7 there. So if I were to ping that address again, does anything change? No, right? So we've got 10.10.10.2. What if I were to say show adjacency detail, right? Now, we've seen the adjacency with just show adjacency here, and it shows the Ethernet interface, and it shows the address. Now, when we take a look at the show adjacency detail, we see something else that's very, very important, and this is kind of what it all boils down to with respect to the adjacency table and the duties and responsibilities it has of rewriting the MAC header information. So, right here in this string, we have the MAC address of the outgoing interface. So if I was to clear my screen and go ahead and say show interface Ethernet 00, what is the burned in MAC address? And we'll do the adjacency detail again. So the burned in MAC address on this interface is AABBCC004200. So do you see that in here somewhere? AABBCC004300. So then, where do you think this address is at? Is it the source address, or you think it's the MAC address on the other router? Well, let's go ahead and go over to the branch and take a look at the interface here, which is show interface Ethernet 00. And sure enough, this is the destination MAC address that we would use from the HQ router's perspective. That is the destination MAC address. So back over here on router, or on the HQ router, when we look at the HQ router, let's re-examine this here. So what appears to be like a random string of characters is actually the what? This is my destination MAC, and then here's the AABBCC004200. This is the source MAC, right? So that's my destination MAC, and yellow is probably not a good choice right there. So destination MAC, source MAC. Now we're just left with this when we're looking at that show adjacency detail. And what do you think that could be? 0x0800. What is that? Well, that identifies the protocol. And 0x0800 is IP. It's the IP protocol, and ARP was how we learned about this information, right? Where is that information being gathered from? It's being gathered from the ARP table. So the show adjacency detail is a very good command to have handy, because you can see the layer 2 rewrite information here for the destination MAC and the source MAC along with the protocol. All right, so let's clear our screen here from the show adjacency detail. And it says on step 3, we're now going to turn EIGRP on, and let's see what kind of different entries we're going to see in the adjacency table when we do that. So we're on the HQ router, and this will be pretty straightforward. We're just basically going to say router EIGRP1, and I'm going to say network 0.0.0.0. So we're just going to fire EIGRP up on every interface we have on the router. Again, not an EIGRP lab, so we're not really concerned with passive interfaces and things like that. We're more concerned with learning, show IP route, some EIGRP routing information. And when we look here, we can see that we're picking up a route with 192.168.110.0/24 from the successor 10.10.10.2. Where are we learning that information from? What is that 192.168.110? It is this network right here behind the branch router. 192.168.110. Let's reinvestigate. Yep, 192.168.110/24. So now let's go ahead and say show Ip Sef. Let's take a look at the Fib, the forwarding information base. So when I say show Ip Sef, do we now have a new entry here for 192.168.110.0/24? We do. And take a look at this here. So the next hop, right? So the Fib is my layer 3 information. It knows that for me to get to the 192.168.110.0/24, my next hop is going to be 10.10.10.2. So how does the fib then make its next decision, right? What happens next? Well, we clear the screen. Let's say show adjacency detail. And sure enough, since I know about the next hop right here, 10, 10, 10, 2, that means I've got an adjacency table entry for that. And what does it give me here again? Right? You've got it. We have our source MAC is here. The destination MAC is here. And there is the protocol, IP. Right? So the fib works hand in hand with the adjacency table, and the adjacency table builds its table with the ARP table information, and that's how Cisco Express Forwarding works. So a packet shows up destined to the 192.168.110.0/24. The packet comes in the ingress interface. The packet then gets looked at, and iOS does a routing table lookup that references the fib, and it sees, hey, I've got an entry for that network, I know the next hop, and I've already pre-computed all of my layer 2 MAC header rewrite information. It's right here. And this is how Cisco Express Forwarding is so much quicker than fast switching or process switching. All right, so we've looked at the fib here, and let me make sure, take one more look at the adjacency table. Let's clear our screen here. So if I were to say show adjacency without the detail, you can see here that we still have this entry that just basically shows that the references have been incremented in terms of the number in the parentheses. All right, so now, how can I tell what kind of switching my interface is doing? If I were to say show IP interface Ethernet 00, when we investigate this output here, you can see that fast switching is enabled. We can also see that CEF is enabled. And there are some cases where the router simply will not be able to use CEF switching, and specifically in cases where you see the receive keyword in the output. And those packets are typically either process switched or fast switched. So when we went back, if I were to say show IP Ceph, remember, we can certainly do Ceph switching with this, because we know that we're going to be referring to the adjacency table that's going to give me the rewrite information. But all of these entries I have that say receive, that means that that's traffic that's coming to the local router. And the receive traffic is not going to be Ceph switched. The receive traffic is either going to be fast switched or process switched, because it's destined for this router. Now, in the output we saw above, we saw that Ceph switching is enabled and that fast switching was also enabled. Now, another command that we can run to see some additional information is just simply show IP Ceph, and I believe it's statistics. Let me see here if they've got it in here. Switching and statistics. So this also shows me some information as to whether or not packets are getting punted to the host, or if they're just simply being punted to the CPU or dropped, right? We could also take a look at show IP Ceph switching, and whoops, we'll pull that back. Show IP Ceph summary, and this just shows me that we have 18 prefixes. So when I say show IP Ceph, this should add up to what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so that's where we see 18 prefixes, right? And so that's the show IP Ceph summary. So let's clear our screen. So now, what if we wanted to disable Ceph switching? on the HQ router. Now, this is typically not something that you want to do because you want to take advantage of CEF. So if I said interface Ethernet 00 and I said no IP route cache CEF, you'll notice that we don't have the adjacency tearing down or anything like that. And so, again, not a destructive command in the context of the routing protocol that we're running, EIGRP. However, if I were to say do show IP interface Ethernet 00, what happens now? Well, now fast switching is enabled and CEF switching is disabled. You can see right here, right? So IP fast switching is enabled and IP CEF switching is disabled. So we've disabled CEF switching. How could we disable fast switching? What if I said no IP route cache? Right? So we did no IP route cache CEF. What if I just say no IP route cache? And sure enough, fast switching is now disabled. So CEF switching is disabled and fast switching is disabled. So these are both disabled. So what kind of switching are we doing at this point? If we're not doing CEF switching and we're not doing fast switching, then we are process switching the packets right now. And again, definitely not something that you want to be doing. You do not want to be doing process switching. For the reasons we discussed in the opening, is that it's just far slower than any of the other switching types. All right, so let's go ahead and we'll say IP route cache, and this turns back on fast switching, and I'll say IP route cache CEF, and that turns CEF switching back on. So let's confirm that. Do show IP interface Ethernet 00, and you can see fast switching is enabled and CEF switching is now enabled as well. Okay, so we can turn it on and off by interface. However, you can also enable and disable CEF. If I were to say do show run include CEF, you can do it globally. So you see where we have IP CEF here? So I've got IP CEF as a command that I can run to enable CEF switching. If I want to turn it off globally, I would simply say no IP CEF and then do show IP CEF. And you can see here that IPv4 CEF is not running. Okay? So it doesn't talk about CEF for IPv6. So let's chat about that for just a quick second. You can see here in the output it says no IPv6 CEF. Well, what if I wanted to enable it? So if I say IPv6 CEF, what do you think it's going to say? Is it going to turn it on immediately, or do you think we're going to have an issue? We have to enable something else. Something we typically have to turn on when we always use IPv6 for our routing. Exactly. IPv6 routing must be on first. Now, here's the trick. If I say IPv6 unicast routing and hit enter, if I say do show run include CEF, do you think that it auto-magically turns on IPv6 CEF? You've got it. It absolutely does. So, and I'll put the IPv4 CEF on. So again, for IPv6, when we go to enable it by saying IPv6 CEF, it's going to give us an error because IPv6 unicast routing is not configured. So you're not going to be able to do IPv6 CEF if you don't have IPv6 unicast routing enabled. And it makes sense. Think about it. Why would I want CEF enabled if I'm not doing for IPv6 if I'm not doing any IPv6 routing? Exactly, you wouldn't. So it's not until you enable IPv6 unicast routing that you then have CEF turn on automatically for you on IPv6. And this, since 1999, CEF has been the default switching paradigm for the majority of the Cisco iOS routing platforms. And today, in the market today, all of the routing platforms that I'm aware of, they are all using CEF for the obvious reasons, and that is clearly performance. But again, if you don't have a lot of your routing information changing all the time, right? It's not necessarily the end of the world if you end up fast switching something. Because again, it's going to cache it, right? And then subsequent packets are going to hit the fast cache. So if you're not thrashing and you don't have hundreds of thousands of routes, you're a small to medium-sized enterprise, fast caching is not the end of the world. However, when we talk about the CCNP curriculum, and specifically you're reading this week Chapter 6, taking a good look at enterprise connectivity to service providers, then it becomes a huge concern, especially if you're taking in tons of routes off of the provider from the internet. And if a lot of that routing information is changing frequently that you have, then you want to be using CEF without a doubt. And so I really enjoyed the coverage that they gave to the topic, and it was a perfect time as well. All right, well, this is going to wrap up Discovery Activity 18. We took a look at CEF. We looked at the Adjacency Table, which is built off the ARP table. We took a look at the Forwarding Information Base, or the Fib, which leverages the Routing Table to construct its information. And basically, the Fib and the Adjacency Table are inextricably linked as part of what makes CEF so efficient and so much faster than either process switching, where every packet hit your CPU, or fast switching, where every first packet to a destination hit your CPU. All right, thanks for watching, and I will see you guys tomorrow evening.